In this lecture, we will cover automation in quality assurance and software testing. What is automation? According to article by Parusaraman, automation equals a system that accomplishes a function that was previously carried out by a human. In other words, automation is a replacement of human effort in, well, basically anything. If we consider land transportation, the first step was obviously walking. After walking, at some point came horses. After horses, and with some industrial revolution, we got cars. And in the latest phase, we are now getting self-driving cars with all sorts of security measures like parking assistant, cross traffic alert, self-parking, blind spot detection, and maybe eventually completely autonomous driving. This basically shows how the automation has increased in land transportation. Of course, one might maybe argue that horse is not really a part of the automation, but from a human perspective, we can consider it to be part of the automation, as it replaces effort previously carried out by a human, although in this case the automation is achieved through, well, not the technical system, but the biological system. If we look into cleaning, well, first there was the sweeper that was just used to manually sweep the trash. At some point, maybe in the 1960s or 1970s, anyway, even before I was born, first vacuum cleaners started to appear. And more recently we have gotten these automated sweepers or automated vacuum cleaner robots that go on the floor and clean the floor completely by themselves. And again, we can see how the automation increases and how it replaces human effort in the area of cleaning. From the examples of land transportation and cleaning, we could start to argue that human history could be seen through the lens of automation. Computing is not really different. If we think of the word computer, it refers to basically automated calculation. The Finnish word ATK, automaattinen tietojen käsittely, is freely translated as automated data processing. The Finnish word for computer, tietokone, is directly translated to English as knowledge machine. So computing is basically just a continuum of this evolution of automation that has been going on throughout the human history. Automation in software engineering. Well, we can start by looking at the automation of programming. In the 1960s, compilers started to appear, and compilers allowed automated generation of assembler code from a higher level language, for example, COBOL. Prior to compilers, all programming was done at assembly code level, which is basically the lowest level of programming. And when compilers appeared, it improved a boost in productivity, as a single higher level programming language line is actually translated to several assembly level programming language lines. For example, concept of loops, for or while loops, do not appear in the assembly level programming language. So having the concepts of for and while loops is highly beneficial as you program in the higher programming languages. And with higher programming languages, I mean programming languages that are higher in the abstraction level hierarchy. Perhaps also some false promises were made in the 1970s and 1960s when it was thought out that managers and business people should be able to read and also write code. And this idea came from the fact that no longer was source code written in the assembly language, but it was written in plain English, as we can see from this SQL example that simply says drop table and insert into T values and what is inserted. This is SQL here on the left. So as this was basically English, the idea was that we can get rid of programmers. Of course, that did not happen. What simply happened is that programmers got more productive and it was perhaps easier to learn how to program. In early 2010, there was a push from ONG with the model-driven engineering, where the idea was that one would only develop models, and then from various models, the code would be automatically generated. Kind of like the idea what was with the compilers in the 19th. So in the OMG model, you would have several independent models like computation model, platform model, and platform-specific model, and from those, the code would then be generated. More recently, GPT-3, the natural language processing AI, is also able to generate source code from natural language. I have linked these videos if you are more interested in looking at how GPT-3 generates code from natural language instructions. Automation in quality assurance in software engineering includes defect data collection, where crash reports are automatically collected from the user's computer to the server where they are analyzed. And we can argue that this has actually brought big quality improvements over the years. 20 years ago, operating systems would crash, all the time, once a day. And 10 years ago, browsers had a similar situation. So web browsers would crash at least once a day or even more frequently. So automated crash reporting systems have been created, which are basically systems that, when a program crashes on your computer, it reports this to a server. So this is this here, for example, is a Windows error reporting server. Once the defect or crash report has been received, it's bucketed so that the different crashes from different reasons can be separated. Then bug reports are made, and people can start debugging this. And this bucketing, also here on the right, is very important, of course, because, for example, in Windows and also for Firefox and many other products, when they would crash often, you would end up having hundreds of thousands or even millions of crash reports. So there needs to be some type of clustering that collects these crash reports to a system. And this is data from Mozilla Firefox crash reporting, but this is about 10 years old. So we can see that the amount of crashes are shown by active daily users. So this indicates how often in a day would a program crash. And we can see different releases. So the stable release crashes the least frequently, only like twice a day, which to modern standards is very high. I don't remember the last time my browser has crashed. And then the pre-releases would crash even more frequently. And then you would see different signatures of the crashes here on the bottom. So how much increases a particular crash signature has increased or decreased. And in a case you want to check how often has your browser been crashing, you can simply do this on Firefox and Chrome by simply typing about and crashes to the URL bar, and then you can see the crash reports on your system. So we can see that, okay, my browser has crashed the last time in 2018. I think this is American date, so this is, I guess, January. Then in October 2017, then It's like 4 times in 2017 September. So here we can see several times a month at least. So the quality improvement is also visible here. So here several crashes per day, and well, the recent data that was only from my computer, it was not from the centralized server, indicated that in my computer it has crashed like no crashes in recent years and a few times a month in 2017, 2018. So going back into this automated crash reporting system, one could then, or one still can, then simply click by particular crash with the particular signature to go and see details of, for example, this virtual alloc exe crash. And then inside of this particular crash, one can see how it has behaved over time. So you can see that, you know, it's pretty low, but then something probably happens with this released on the November 2nd, and then the crashes go up. And you can see that something was obviously wrong in this release, particularly for the Windows, not so much for the others. And this is normalized for the active daily users. So, oh wait, excuse me. Oh, this is just an actual number, so it might simply highlight that Windows is more frequent. But we can see no increase in other platforms. And then one can go through the reports of seeing individual. If you go to the tab reports, you can go and look at the individual crash reports. You know, and this is a single crash report coming from a particular computer, a particular date and time. And if one also clicks through that, then even more detailed information is provided. This is kind of like the information that was shown also to be important in the defect reporting in the previous lecture. So, you know, product of the software and context information is given. Crashing threads, other threads, also not visible on the screen, but one could also browse through what libraries have been loaded and so on. And basically what all this allows when you collect a lot of crash data is that you can sort of do statistical debugging. For example, you can look at correlations. If a particular library has been loaded, is this crash more or less frequent? And then you can make educated guesses on whether the particular bug is related to some library being in the memory or not. And these are reports coming from the field. So this is automated data collection from the users. And there have been other proposals as well. So this is from an academic paper from 2016, and what they had built is basically automated headless testing and reporting of crashes in Android. And basically headless testing means that you have not pre-programmed the test cases. As the test cases have not been pre-programmed, there is still there's a decision engine that determines the next action in the graphical user interface and in the event execution. And so it decides what to do next based on the stuff that's on the screen and based on some heuristics, and then it executes the action. After executing the action in a physical device or in an emulator, it analyzes what happened. It goes through different automation, takes screenshot, component information, touch event, GUI event, and determines if there is a crash. If there is not a crash, the execution continues. The execution can also finish on its own if, for example, a time limit expires. But that's not so interesting. So if there is a crash, it saves the execution information to a database. And then it automatically generates a report on what had happened. And this report generation is a similar in principle to what we saw on automated defect reporting. So basically, after it has successfully generated a crash, it does automated defect reporting. So it collects all the information available in the device and then sends it to a database. It also does execution script replayer. So it also records the script that was able to achieve the crash. So this way, when the defect report is analyzed, the developer can look into the device information, but it also knows what steps did the decision engine do to cause this crash in a system. So now one might think that okay, testing has been solved, but this is not really the case, because the problem here is that, well, it can only figure out if the system crashed or not. So that is basically the only type of defect it is able to detect. So it can detect whether the system crashed or not. It cannot detect any other type of defect. So if there is other malfunctionalities in the Android application or in the device, it cannot detect that. Another possible issue here is that this is an academic prototype that works like maybe on one device. And also maintaining this is not very cheap. So when new Android software is released, one has to update everything and hope that it still works. However, this does demonstrate on where we are heading in software testing and error data collection. So now we have shown automated defect data collection and also automated testing to some detail. But also there is an active research field known as automated program repair that attempts to fix programs automatically when defects are detected. And automated programming repair is based on the technique known as fault localization. So it relies on the fact that you have a very extensive automated test suite that is able to detect defects. Then it basically uses information from the version control to figure out what has changed in the previous program, and then it also executes all the tests and figure out what statement is the most likely to be the source of this error. And from this it produces a statement ranking. So this is the first statement would be the one that is the highest, has the highest probability of generating, of being the reason why the program is now buggy. And after that it performs manipulations, automated program manipulations on that line. And it does some manipulation and then it validates the patch. So if the patch validation basically means it reruns all the tests after making some manipulation on the source code statement. So if the patch doesn't go through, it still fails, it manipulates the same statement again, perhaps with a different type of manipulation, and so on. And then at some point it moves on to the second statement. And every time it runs all the tests. And finally, the patch is validated by when all the tests go green again, when all the tests are working. So basically it tries all sorts of fixes to the statements, and then at some point the machine actually succeeds, because there is some focusing on certain statements on where the manipulation should be made, and this focusing is based on the fault localization technique. Of course, this type of this program repair is heavily dependent on that one has a good test suite, automated test suite. If one does not, then this cannot really work. So to summarize, I have went over some automation areas in software engineering and quality assurance. First we covered automated programming. Then we covered automated error or crash reporting. We covered briefly automated testing, but more is coming in the next video clips, and then briefly looked into what is automated program repair.